Okay, determining the size of an object on a microscope. Now, before I fill in these blanks, let's take a look right here. These are some microscope images that I just took from online somewhere. Obviously, it's an American penny. And you can tell just by looking at this, which one of these things is a low power view. Yep, the top left. It's got the lowest magnification. This is low, right? And which one is the highest power magnification? Yep, bottom right. This one is high, all right? Now, when we zoom in from low to high, and that's essentially what we're doing. You can think of it like on your phones these days, how you pinch and zoom into something. So when we're switching to low, medium, and high, it's like we're zooming in on that object. Here you can see, right, a large area of space. So you can see a large area under low power. So under low power, you see a large area. But when you zoom in, you see what happens to the amount of area that you can see. You see a smaller area. So notice here, the area that we're seeing under the high is probably that big. So when you zoom in, you can see more details, which is good. That's what we want to see as biologists. But you see less of the area. So you actually see, right, a smaller area there. So let's go back and fill in our blanks here. Back. When you look at a microscope, you see, well, all I wanted there was a circle. A circle. You see a circle. Now that circle is called, and I actually used this the other day. Does anybody remember what it's called? That circle, this area is called the blank of blank. And I said it yesterday. Yeah? Field of view. This is called the field of view. Whenever you look in any optical device, what you see is the field of view. A telescope, what you can see is in the field of view. When you change to a higher magnification or higher power, so I'm going to put here just magnification, you see more this, but less this. What do you see more of? Less, I'm going to put area, but you're right, space. It's like it's a flat area. So you see more detail and less area, less space. So it works like this. If I have a greater magnification, if the magnification is a big number, all right? If the magnification is a big number, what does it do to the area? A bigger magnification makes a smaller area. In science, we say that they're related inversely. They do opposite things. When we zoom into a greater magnification, we actually see a smaller area. Okay, so let's then talk about how we're going to calculate this. When we try to figure out how big something is on a microscope, we need to do two steps. We need to do a calculation to figure out how big the field of view is, so how big that is, and then we estimate what we want to look at. So it's two steps. First, we calculate how big the field of view is, then we estimate how many of those things that can fit on there. Let's first talk about the calculation. This is the equation that we use in order to calculate it. The D stands for diameter. What's the diameter of a shape? What's the diameter of that? Yep. No. What do we call half of the circle? The radius. So the diameter is how far across. Okay? So the diameter is how far across our field of view. M stands for, well, what do you think it stands for? What have we been talking about when talking about microscopes? Magnification. Magnification. The magnification is 40 times, 100 times, 400 times. Again, my notes are not that funny. Excellent. When we rearrange this equation, this one right here allows us to find how the diameter changes when we have a different magnification. So this says the diameter of the high is equal to the diameter of the low, if we know what the low is, and then we have to multiply it by the magnification of the low divided by the magnification of the high. Notice these letters. Notice the letters are opposite. Diameter high, diameter low, magnification low, magnification high. So diameter high is equal to diameter low times magnification low, both L's, divided by the magnification high. So diameter high, take the two L's, take the two L numbers, multiply them together, and divide it by the other high number. Okay? And that's how you get the diameter of the high. We would get the same with medium, except I would just put M in the place of H for the medium power. Let's do a few practice calculations. So, when we do our next lab, and it's not going to happen today, I don't think we're going to get done it, but tomorrow we will start by looking at the how big a human hair is, the diameter of a hair. The first thing we have to do, though, is we have to figure out how big our field of view is. Now, this picture right here is representing a millimeter ruler, just like the rulers we've been using, and we're going to use these rulers. If I put a ruler under the microscope and I put it under the 40 power, I get about that many markings, approximately that many. It'll be different for our microscopes because it might be a different power. And you can see there, I can actually count millimeters across the field of view. 1, 2, 3, 4, and probably a half and a half, probably 5 millimeters across that field of view. That's the diameter of that low power. Notice when we zoom in. When we zoom in, we can't actually determine how many millimeters there are, so I can't actually use my ruler to measure the high power field of view, because all I'll get is like a big fat line. Just like when we looked at the letter E and we got like a big fat piece of the E. So what we can do is we can measure how big the field of view is under low power, and we can use that equation to figure out what the field of view is under high power. So let's take a look at this. The diameter under low power is 4.5 millimeters. Okay? I said 5, but I agree. 4.5 is pretty good. It's about 4.5. This is the same as blank micrometers. Remember yesterday, how many little micrometers did I say was in a millimeter? No, it wasn't 10. 1,000. 1,000. 4,500. So this is the same as 4,500 micrometers. So under low power, for this example, it's 4,500 micrometers. If the magnification under low is 40, and if the magnification under high is 400, how wide is it here? Well, let's use our equation. D high is equal to, what did I have on the top? If I'm looking for the high number, what letters were on the top? ML and? Well, hold on, I want the both variables that were on the top. Yep. DL and ML, the L values were on the top. DL and ML. And then the other M, right, because there's two of each, M high is on the bottom. See how that works? If I'm looking for high, the two L's are on the top and the other high is on the bottom. When we do this on a test, I'm going to let you have that equation. That's not a big deal. But for now, you're going to have to, when we do our practice sheet, you're going to have to pull it out of your note that you're writing. DL. What's the diameter under low? What's its length under low? The diameter of the low. Yep. And let's do it in micrometers. 4,500 micrometers. 4,500 micrometers. You could do it in millimeters. Your answer would be in millimeters. But we want it in micrometers. What's the magnification of low? What's the low? 40. What's the magnification of high? 400. We all know if I put it in brackets like that, that's a multiplication, right? Are we okay with that type of math? So we're okay with 4,500 times 40 divided by 400? Could somebody do that? I don't know if you've got a device nearby that can do that calculation. 4,500 times 40 divided by 400. Yeah, what do you got? 450, and what unit would that be? Not millimeters. Micrometers. That funny U and an M. 450 micrometers. What's that? It's actually it's not actually a U. It's a Greek letter, and the Greek letter is pronounced mu, like a cat. You know what I mean? Like mew. But that's the Greek letter, and because it's an M in Greek, all right, we use it for micro. I can't use a regular M because that's used for milli. So what the measuring guys invented was that Greek letter M, which is mu. It's kind of a goofy letter. So 450 micrometers. So that's how we can do it for each of the different powers. If I wanted to do medium, it would be 4,500 times 40, the low power, divided by what? What would go on the bottom if I wanted to study the medium power? What would go on the bottom this time? 100. So it would be 4,500 times 40 divided by 100, and that would get me the width of the medium power one. Okay? All right. So that's how we determine that. Let's do a little practice run here. Let's just do another example. Some of you might be ahead of me. Let's say that we have a certain type of microscope, and we measure it, and it is 3.3 millimeters. Sorry, not 3.3, 3.0 millimeters. How many micrometers is that? Hands up. How many micrometers is 3 millimeters? Yep, 3,000. And I put the little tail on it. What is the diameter of the field of view under the medium power this time? Now notice I gave you the low and I gave you the medium. Now, we could write an equation that says diameter of the medium, but you don't have to. It could mean the diameter of the higher power. You know what I mean? Because it's higher than it. It's higher than low power. So I'd like to keep the H, but you don't have to. You could put an M, but I'd like to keep the H because I'm really talking about what's the diameter under the higher power. DH. What goes on the top of that equation? What goes on the top of that equation? What goes on the top? I don't want the numbers yet. I want the symbols. If this is H, what goes on the top here? I need a DL. I need an ML. Remember, it's the two L's and then MH. L's and then H. Right? So the L's go on the opposite goes on the top. Now tell me what to put in my equation here. What is the diameter of the low power objective? No, this is a new question. What's the diameter of the low power objective? Diameter under low power is 3 millimeters. We want to write it as 3,000 micrometers. Magnification under low. 40. Magnification under high, or higher. Not in this case. I want to determine what the field of view is under this case, 100. So, well, higher power. Higher power. Not necessarily the high power. Higher power. It's higher than the low one. Does that make sense? Okay. Like I said, you could change those H's to M's if you'd like, but you don't have to. How wide is that medium power thing going to be? Did you calculate it out? 1,200? 1,200 micrometers. Okay? Take the diameter of the low, multiply it by the power of the low, divide it by the power of the high. So that's how we determine how big it is. The second part is estimation. So let's say that we looked into a microscope and we saw two cells like this. Now that would be perfect. See how they line up perfectly? They line up perfectly to fit perfectly. The way we determine the width of the object is to estimate how many of those objects fit across the field of view. So let's say, for example, let's say for this example here, that this has a diameter across it of 1,200 micrometers. Let's say it's 1,200 across. How many of my cells fit across this field of view? By the way, this is a cell. How many of my objects fit across my field of view? 2. And that's why I knew it needed a better definition. So I've got 2 objects that fit across. How big is each object? Half of 1,200? 600? You see what I'm saying? So if you've got an object that fits 2 of them across, you simply take what it is across the whole thing and divide it by the number. So in this case, the width of the object will be, the width will be the diameter of the field of view, 1,200 micrometers, divided by 2, because 2 of them fit across. So these things are approximately 600 micrometers each. Actually, it's not even approximately. I built this picture to fit 2 of them across perfectly. But in a real microscope, it's not going to fit perfectly. We're going to have to estimate it. So let's do one more as a practice, and then I'll let you start working on the worksheet. Okay, and the worksheet is doing the same type calculations that we just did. So let's just do one more here. We just did that one. Let's look at this one. So we just did the 2 circles. I did it up on the front there. Now let's look at this. Here I've tried to draw a cell. It's got a little nucleus in there. Very simple cell, maybe, that we're going to look at. We are under high power. So the field of view is 450 micrometers across. The question becomes, how many of these fit in my field of view? If I want the width, which is the wide one, not the long one, if I want the width, how many fit across? Yep. About 4. 1, 2, 3, 4, maybe 4.5, but I would say 4. I would say 4 divided by 4. So how wide is each of these cells? Who do you need?
Justin and Tyson.
Justin and Tyson, you guys go out the back door. There's a worksheet that you guys got to work on. It's on Google Classroom. That's going to be turned in. Okay?
Thank you very much.
Yeah. So we figure 4, about 4 of them. See how we estimated that? So that's the estimation part. We've calculated that the field of view is 450 micrometers. So about how wide is this cell? Yep. Now, 112.5, to get down to the 0.5 is pretty definite. Remember, we estimated that it was about 4. I think if we said that it's about 112 micrometers, that would be great. You could write 112.5, that'd be fine. But we really don't, you know, we did an estimation. Okay, so we calculate using that equation to get the field of view, and then we estimate how many fit. All right, so that's the end of the slideshow. I am going to stop my video. If you go to now the entry above it, it says there's a worksheet where you're going to then do some calculations, and you're going to be getting some numbers. It's the same type of calculations that we just did. Once I get this going and uploading, I'll come around and I'll make sure we're on the right track. I just got to get this saved. Again, if you want to write the answers on a piece of paper, you can do that. But you can just write it on this thing and you can just submit it there.